Okay, let's talk about section 6.2. Like in the previous section, like during the class, we talked about the definition of the Laplace transform, and we talked about a couple of important property, which is the existence and linearity, right? So like from section 6.2, we're going to talk about how we can use Laplace transform to solve the differential equation, okay? As I mentioned like in the previous class, um, Laplace transform is much more general method to solve differential equation, okay? So, well, like, some problems are like possible to be solved by the previous method and this one as well, okay? But it's really up to you. But, this is like, really important practice to solve like much more general form, okay? So to use Laplace transform, we have to talk about like a couple of important property of Laplace transform, okay? The first one is lifting. This is really important for solving the differential equation, okay? So here we go. First of all, your function f is continuous, and another important part is your f prime must be piecewise continuous, okay? And in a given interval, okay? And another one is like, we already talked about this one, right? This is the exponential order, right? And your function, absolute value of your function must have like, k times e to the a t4, okay? Then we guarantee like you must have Laplace transform of your function, right? And then like the more important thing is this one. We're gonna say this is lifting. Laplace transform of your f prime function can be written by s times Laplace transform of f of t minus f of 0. Okay, so if I say um, s like that, then this can be written by s fs minus f of 0. Okay, and like for here, like the Laplace transform method, um, like, your initial condition must be defined at t equal to 0 only. Okay, that's really important. Okay, so well, like you're gonna like remember, you memorize this lifting like to solve the problem. But like since this is math course and I'm mathematician, I would like to show you how we can prove this. Okay, it's really easy. Like whenever you prove something theorem, then we have to use definition. Okay, here we go. So let me start from Laplace transform of f prime of t, right? By the definition, it is equal to integral 0 to infinite e to the minus st times your function, which is a prime of t dt, right? So well, if here, definitely we're gonna use the like integrating by part. Okay, let's say this is du. Mm, okay, let's not just this way. U is at prime. Oh no, what am I doing? U is e to the minus st, then du is minus s e to the minus st, and let's say dv is f prime, then v is just simply f, right? Uh, then integrating by part, this can be written by e to the minus st times function f, and minus and plus integral s e s t f dt, right? So look at this one. In this integral, like t is the variable, then s is constant, right? Then this can be written by e to the minus st and ft plus s times integral e to the minus st f dt. That means 0 to infinity, right? Okay, we're going to 0 to infinity for the first one as well. But do you remember that is exactly the definition of Laplace transform of, right? Does it make sense? Okay. Then, okay, now Oh, and also you have to take care of this one as 0 to infinity as well. Then that is equal to, when you plug infinite, e to the infinite, well, like we say s is positive, so like your exponent part is negative, then e to the negative power is equal to 0, right? So that would be 0. When you plug in 0 is f of 0, right? So that part is negative f of 0. And then what about the second part? Plus s Laplace transform of f of t, okay? Let me just reorder this, okay? It is s times Laplace transform of f of t and minus f of 0, okay? That's exactly what I said, right? It is lifting, okay? So, well, not only for f prime, but also we have to extend. We can extend to f double prime as well. It is given here, okay? If you want to find the Laplace transform of f double prime, it is given like this way. That's really easy. Here we go. Since we know the double prime is prime of first prime, you know what I'm saying, right? Laplace transform of right? Then let me apply the previous one, okay? So previous one we said it is equal to s times Laplace transform of f prime t, because that is original function, and minus f prime of 0, right? Then let me plug in this one with like the first order lifting as well, s Laplace transform of f of t minus f of 0, right? Then this can be written by s times s Laplace transform of f of t and minus f of 0 and minus f prime of 0. So which is equal to s squared Laplace transform of f of t minus s times f of 0 minus f prime of 0. That's it, okay? This is the way to extend your lifting property, okay? And like, what about the minimum number, the other number 7? Well, it is general form, okay? It is general form. So like you can extend like, as much as you need, okay? So actually, like, you have to memorize this one, but fortunately, as I told you, like for this chapter, we're gonna use this table. On the bottom of table, uh, here we go, number 18. What is that? Uh, the lifting property is stated here, okay? This is lifting. So you can use this lifting property, number 18, like from the table, okay? Thank you.